What's up, everyone? Welcome to AP Statistics. In this video, we are going to focus on organizing data from one quantitative variable. All right, so in this video, we're going to specifically be looking at one variable, quantitative variable. So an example could be looking at the height in feet of a tree. Height, it's a number, feet, it's a unit. Those are quantitative variable there. We also discussed comparing the same variable between two different populations. So maybe we're going to, again, the idea here is one variable, but comparing between two populations. So the height of maple trees versus the height of oak trees. So we're still looking at height of a tree. We're just comparing it between two different populations. What we will not be doing in this video is examining the relationship between two quantitative variables. How does one quantitative variable change another? Not looking at that. That is, of course, coming soon. So in this video, we're sticking with one variable, but we might be comparing it between two different groups. All right, there are many ways to display a quantitative variable with a graph. A lot more options here than we have with categorical data. So deciding which to use is very important. One way is to help to identify which type of quantitative variable you're working with. Yeah, we have learned that there are two types of variables, but when it comes to quantitative, there are also two different types that fall underneath that. So the two specific different types of quantitative variables are discrete quantitative variables and continuous quantitative variables. Now, a discrete variable can take on a countable number of values. Think about the number of values may be finite or countably infinite, as with counting numbers. So I don't want to make they sound hard, I don't want to make this harder than it sounds, but think of here if you could list the possible values of the variable, it's countable. So typically we are thinking about whole numbers here. For example, how many wins could a soccer team get? I mean, that's not infinite, right? A soccer team could get 0 wins, 1, 2, 3, 4, 5. At some point you're limited. Could a soccer team get 100 wins in one season? I mean, I don't know any team that plays that many games, right? So only whole numbers. A soccer team can't win 2.5 games. It doesn't make sense. Another example could be counting the number of Skittles in a bag. 1 Skittle, 2 Skittles. Oh, there's 55 Skittles in a bag. Again, whole numbers only, and you can't have an infinite number of Skittles in a bag. Counting the days, the number of times a geyser erupts per day. So maybe you go to a geyser, Old Faithful in Yellowstone Park, and you count it erupted 5 times that day. Again, it can't erupt 1.8 times. It doesn't even make sense. And it certainly can't erupt an infinite number of times in a day. So that's a discrete variable, discrete quantitative variable, still quantitative. The second type is a continuous variable. And here, a continuous variable can take on infinitely many values. So we're not just talking about whole numbers. We're talking about literally any decimal values. And when you start to consider the fact that you could go to the 10th decimal place, I mean, there really is an infinite number of values that this variable could take on. So example here could be the height of a student. Once again, decimals are in play. Somebody could be 65.5 inches tall. But if you really want to get a magnifying glass and zoom in, you could be 65.543 inches tall, and somebody else could be 65.534 inches tall. So when you start to think about including decimals, you start to realize, oh my gosh, there's infinite possibilities when it comes to the height of a student. Concentration of salt in a water sample. If you measure salt in a sense where you say, oh, there's 5.6 milligrams of salt, or another unit of measurement for concentration is parts per million. There's 3.9 parts per million salt in the water. So again, you got decimals. And when you start to think about decimals, the moment a value could be a decimal, now you think that's really infinite because of how many decimal places there are. Even if you're limited, like even if you just say the options are from 2 to 4, oh my gosh, when you think about decimals, there are infinite number of values from 2 to 4. So that's a continuous variable. All right, so now let's kind of get into ways that we could display these different things. There's really are quite a few of them. And the first is kind of like a categorical variable. We have this frequency table. So here is a frequency table. Now, since there are so many outcomes for a quantitative variable, we typically have to create intervals or bins. So with categorical data, you say chocolate ice cream, 15 people liked it. Vanilla, 13. But when you're talking about a quantitative variable, there's a lot of outcomes. So we create intervals, or I like to call them bins. So for example, if we're looking at the height of a bunch of trees. So we say, well, boy, there were 18 trees from 10 to 20 feet. So that means we create this bin, 10 to 20, and any tree that measured 10 to 20 feet tall fell into that bin. So again, frequency is a count. We counted 18 trees that fell into that height. Now, it's important that you understand that anytime we create intervals in this class, we call them left-handed intervals, meaning that you equal the left side, you go up 2. So this bin is technically 10 feet up to 19.9999999. So if a tree is 20 feet, then that tree would go into this next bin. So we're always left-handed, which means we equal the number on the left side, but we go up all the way up to the number on the right side. But again, 29.99999 cannot be written, so that's why we say 30, but we know that that bin is 20 up to 30. So once again, 40 trees were counted that were 20 to 30 feet tall, and then so forth down the line. So the frequencies are still the counts, just like they were with categorical data. But again, we create these intervals. So these are intervals for those quantitative variables. So it's super important for you to understand that when we examine, for example, the 8 trees that were 70 to 80 feet tall, just looking at this table, we actually don't know what those trees were. They could have all been 75 feet, or there could have been a 71, a 72, a 73.4, a 76.9. I mean, we don't know. All we know is that there were 8 trees that fell into that interval. Without seeing the actual list of all the different heights of the 175 trees, I don't know the exact heights, just that 8 of them fell into that interval or that bin. Now, of course, we could take any frequency and turn it into a count, or turn it into a relative frequency by just dividing by its total 175. So that tells me that 10.3% of trees were 10 to 20 feet tall, 24% of trees were 30 to 40 feet tall, all the way down the line, 4.6% of trees in my sample were 70 to 80 feet tall. So again, that's a nice way that we can organize a frequency table for quantitative data. But again, really want to emphasize that we have to create these bins, and notice that all the bins are of equal size. I went with 10 feet. You can make more bins and go by 5 feet, 10 to 15, 15 to 20, 25. You can make less bins by going 10 to 40 or whatever, but that's what I decided to do for these problems. Hopefully that makes sense. Okay, now we really want to start diving into the types of graphs that we could have. Okay, now all graphs, you got to have a number line. Remember, quantitative data, these are numerical values that can be put in order. So we always need a number line. Typically, it's going to be our horizontal axis, but not always, as you'll see here. And how you make the intervals, not number line, is really up to you, kind of like I did with that frequency table, but you got to stay consistent. So all of these graphs represent the distribution of the data. It's important that the word distribution, that you know what that means. The distribution of a variable is simply what values the variable took on and how often it takes those values on. So you're literally just showing, hey, these are the values that I saw in my data, and these ones were most common. Now, the first way we could do this is with a dot plot. A dot plot is really best for discrete variables where they're whole numbers only, and every dot represents an individual. So imagine I asked 14 kids, hey, how many hours a week do they exercise and how many hours a week do you play video games? So in both of these graphs, every dot represents a kid and how many hours they exercise in blue, how many hours they played video games in green. So this particular kid played per week, 14 hours per week of playing video games. This kid right here, now notice there were 2 kids right here at 3. So 2 kids exercise 3 hours a week. So when we had another person that also exercised 3 hours a week, we just stacked them on top like that. So once again, we get a feel for the distribution. We see what values were taken on. Looks like 0 to 12 for exercise, but we see what values were most common. Most common was really 1 to 3 hours per week, even though a couple kids did a little bit more. Here's another example of a dot plot. This was where we took a ping pong ball and we put in a catapult. You guys know what a catapult is, like a little miniature catapult. And we launched the ping pong ball and we recorded the distance that that ball traveled. So once again, notice here that my intervals go by 4, but I also put tick marks for all the numbers in between. So you would read in between the lines 9, 10, 11, 13, 14, 15, and so forth. So you don't have to label all of them, but whatever you decide to go, be consistent. So once again, for example, we saw 1, 2, 3, 4, 5 ping pong balls that went 21 feet. So 5 times I launched this catapult and the ping pong landed 21 feet from where I launched it. The max all the way over here was twice. I went all the way to 32 feet. And looks like once, for some reason, the ping pong ball only went to 9 feet. But again, what this allows me to see is the distribution. What values my variable took on and which ones were most often occurring. All right, the next type of graph is a stem and leaf plot, which you should be fairly familiar with. The stems are our intervals and the leaves are the values. So once again, stem and leaves plot, these could kind of go either way, vertically or horizontally, but typically they go vertically. But again, this 3 represents an interval of any data falling in the 3s or the 4s or the 5s. But again, the key is really needed so you know how this works, right? And then the leaves over on the right side are the extra value afterwards. So, for example, the key tells me that 8/0 is an 80. So these values are 34, another 34, and a 35. So stem and leaf plots are kind of cool because you can actually see the data values in the table. You actually see the data values. So it's actually very much like a dot plot, but instead of putting a dot where the value fell, we actually put the number. So 34, 34, 35, 52. Keep in mind they do have to go in order. And then again, when you get into double digits, this number all the way down here would be 150. So you really need to make sure you understand that value. So by the way, this would data represent the final price of 24 stocks. So this particular stock was $150 per stock. 2 stocks were $89. So again, this is a great way to see that distribution. We see what values the variable took on. What were the price of the stocks? Well, it looks about $34 to $150, but we also see what values were most common. Looks like anywhere from $60 to $80 was the most common price of a stock at the end of the day. The nice thing about these is you actually see the data, which is kind of cool. But that key is super important. Here's another one. This is actually called a back-to-back stem plot that allows us to compare the same variable across 2 populations. So here the question was, how many hours does a battery on a phone last until it dies? We have brand A, maybe this is our Samsung Galaxy Plus. Brand B, maybe that's our iPhone, who knows? But again, now we see 1 leaves on the left, another set of leaves on the right. But the key here is really important. Once again, these numbers are in hours. So the 0, that actually be 7 hours. So 1 battery only lasted 7 hours for brand B. For brand A, we had 5, a 7, 8, 8. And then again, now we get into the 10s. For brand B, we had a 10 hours, 15, 15, another 15, a 17, and 19, and so forth. Just be careful that you always start with the stem. So this is 75, and this one is 61. I'll get some kids that will read that as a 16 because they just get used to reading left to right. Always start with the stem, even if it's in the middle. So brand B had the battery. 1 battery lasted the longest. My gosh, 75 hours. But brand A's longest was 61 hours. Once again, we can compare them, which is awesome. But we see the distribution. We see what values the variable takes on and how often it takes on those variables. So for the most part, you take away a couple of these outliers, we see that most of the times the batteries are lasting anywhere from 10 to 40 hours. Now we could even do what's called a split stem. This is kind of nice to do. This is basically like splitting your intervals, right? Like, for example, I could have went intervals of 10 to 20 for my tree problem, but I could have went, 10 to 15, then 15 to 20, right? I could go by 10s or I can go by 5s. So that's essentially what we're doing when we call it split stems. So this stem right here is for the lower 10s. This is for the upper. So we split that at 5, right? So for example, if we're splitting up the teens, right? This would be 10 through 14. That's 5 values. This would be 15 through 19. So again, 15, 17, 19, 19. Oh, by the way, this data was how many windows does a house have? That would be a discrete variable. Can't have a decimal amount of windows, and you really couldn't have an infinite number of windows on a house. So again, this house had 7. Another house had 9. Down here, 2 houses had 27. But again, we're splitting the stems. All that's doing is just separating our data a little more, creating more bins. But it doesn't change how you read and look at that. All right, the last way, and I don't want to toot its horn, but this is really, I don't want to say it's the best, but the most common way to display a quantitative variables with a histogram. Now, the first thing I want to actually mention is that a histogram looks, smells like a bar graph, but it's not a bar graph. I can't emphasize enough that bar graphs are only for categorical data. That phrase, that word, that vocabulary term, bar graph is only for categorical variable. Anytime you use bars to represent quantitative variables, this is a histogram. Has nothing to do with history class, by the way. Okay, so once again, if you remember all the way back from the very beginning of this video, I showed you that frequency table for the heights of 175 trees. This is a bar graph, but I don't want to call it that, right? I know it looks like that. It's hard to get used to. But a histogram is simply just showing the heights or the counts of the number of trees in each of the intervals. So remember, my intervals went 10 to 20. Once again, left-handed intervals. So this is 10 feet up to 19.99999. So I see that quite a few trees fell into that bin. This bin right here was from 20 to 30 feet. I see 40 trees fell into that bin. 40 trees were 20 to 30. Now, I know I made this in Google Sheets, and there really should be no gap because where 19.99999 stops, 20 picks up. So there really should not be a gap here, but I tried everything I could, but Google Sheets just puts that gap there. I wish they didn't. I get so angry that they do. But again, whatever bin size you decide to go with, you got to stay consistent. I went with 10s. You could go with less and go by 15s or go by 20 and have less bins. Or you could separate it even more and go by 5s or even 2s, 10 to 12, 12 to 14, 14 to 16, and have more bins. It all depends how you want it to look. Oftentimes you don't want too few bins, but you also don't want too many. You're trying to find a nice balance. And for this data, 10 makes it look really nice. Now, once again, I can't emphasize the drawback or the one negative here is, for example, I know that there are about 42 trees in the bin 30 to 40. But what are the heights of those trees? Without the data in front of me, I don't know. All I know is that 42 trees were in the bin 30 to 40. To be quite honest, every single one of those trees could have been 31.5 feet tall. I really don't know. They could have all been. All I know is that 42 trees fell into that range or that bin or that interval, okay? But histograms are really cool. They do a great job of showing us the distribution. Remember what a distribution is. It's showing us what values the variable took on. Looks like anywhere from 10 to 80 feet. But it also shows us what was most common. 30 to 40 was the most common height of a tree in my data. All right, histograms are the most popular, right? We see histograms all the time. But you got to be super careful with all the details. You have to label your axes. What are your units on the bottom? Feet, height of a tree in feet. Always have units. On the left-hand side, the vertical axes is it a count? Does each bar represent the count, how many trees, or the proportion? Because you could also make a relative histogram where the bars represent the proportion of trees that fell into that. The interval sizes, the actual bins, they must be equal in size. So again, I chose to go by 10s. You can't have some bins go by 10 and others go by 8. That's just silly. An empty interval simply tells you that there's no data values falling into that interval. So for example, if the 30 to 40 bin was just empty, there was no bar there, it doesn't mean we made a mistake. It just means that no trees were of that size. I want to emphasize for the third time, left-handed intervals. We equal the left number up to the right side. Important not to forget that. Now, if it is a proportion or a relative histogram, you only know the proportions, once again, not the actual counts. The same issue we have with categorical data. If I tell you that 12.5% of trees fall into a bin, you don't know actually how many trees unless you know your total. So be careful. And the number one thing I want to say again, the only bad thing about a histogram is that you do not know the actual data values. You just know how many fall into each bin. So let's look at several more examples because histograms are so popular. I just want to show you guys a bunch of different kinds. Here's another one where we looked at 26 different chimpanzees and we measured how long it took them to solve a puzzle. So notice here, my bins are by 10, but I didn't write them all, and that's okay. It can be applied. So that'd be 10, 30, 40, 50, 60, 70, 80, 90. So you got to be able to read. But again, make sure that you also, again, this is, I'm sorry, I'm trying to get ahead of myself a little bit here. But what this shows me is that 6 monkeys spent 0 to 10 minutes to solve that puzzle. How long did it actually take those 6 monkeys? Without the data in front of me, I don't know. 5 minutes, 4 minutes, 9 minutes, 9.5 minutes? This would actually be continuous. When you're working with time, that's a continuous variable because there's so many options when you think about decimals. But again, you see the different times that were possible and which ones were most common. We do see one monkey took over 90 minutes. Here's another one where we try to make it some different colors to jazz it up. But here's are the heights of 30 random people. And these values were in centimeters. Notice you always want to have units done on that horizontal axis. And then up the side here, we have frequencies. So that would be the counts, how many people. And notice my bin sizes were going by tens. Kind of weird. They went 139.5 to 149.5. But it is what it is. At least they were consistent. And again, we see 9 people fell into the bin, 149.5 to 159.5. So again, another beautiful histogram there. All right, here's another one with the grades of students on a test. So once again, this one's not labeled too well. So here's 10, 20, 30, 40. That's another drop back to histogram. Sometimes you kind of have to eyeball how many, like if it's not super clear, like for example, how many kids scored 40 to 50 on the quiz? I don't know, 12? It's kind of hard to read, maybe 13. You're kind of doing a little bit of guessing at that point. But again, left-handed bins. This bin is for 70 up to 79.9999. And it looks like maybe 44-ish. Again, that's another one of the bad things. If you can make a short list of bad things for a histogram, is sometimes you got to guesstimate a little bit. But I can't, I've said this for the 8th time. I'm sorry, but I want to make sure you hear me. All I know is that 44 kids fell into the bin 70 to 80. What were those kids' test scores? I don't know. I just know that they were from 70 to 80. And here is one more, another one here. These were actually your heights. Yep, I took the heights of you guys, my AP Stat students, and I made a histogram of your heights. And I went by 2s. Each bin went by 2 inches. And we see that, a small amount of kids were 60 to 62 inches tall. The most common occurring, it was kind of the most common, was kind of really 62 to 68 is where we saw a big chunk of kids. Here's a couple of my taller students that were 74 to 76 inches tall. That is a continuous variable because when you actually, if I really wanted to get serious with the measuring tool and measure your heights, I could really get down to maybe the 4th or 5th decimal place in terms of how tall you are. But again, when you make these in Google Sheets, it puts those little teeny gaps in between the bars. I really don't like that, but they're there. Now, here is something else I did. This is even cooler, right? I took your heights, and now I separated males on the left, females on the right. So I'm still looking at height. I'm still looking at one variable, but now I'm comparing them. I'm not looking at the relationship between these variables. I'm just comparing them. In fact, one of the variables is categorical, male, female. But anyway, now this allows me to compare and see, ooh, okay, males are typically taller than females. Let me just look at the data, right? Most of the females are around 62 to 60 inches tall, whereas most of the males are around 70 to 74 inches tall. And that's pretty typical, right? We know that males generally are taller than females. But again, separating it really allows me to see that great distribution here for the males and for the females. And here is one more for you guys. Here's another one. I wanted to show you this one because this one is relative. We haven't seen a relative one yet. So this just took how many people were in each bin divided by the total to get a percentage. So for example, we know that 40%, 40% of people in this survey were 65.95 to 67.95. Kind of a weird interval there, but hey, whatever. The intervals go by 2. That's how many people fell into that height range, 40%. But once again, if I don't know the sample size, we talked about this with categorical data. If I don't know the sample size, All I know is that 40% of people in my survey were in that bin, in that height range. I don't know actually how many. I mean, if I had 100 people, that would be 40. If I had 1,000 people, that would be 400, right? So 40% could be a very different amount of people, all depending on my sample size, which unfortunately I don't know. But I just want to make sure that you saw that, read the vertical axis here. You could have a histogram that shows the percentage relative frequency in each bin as opposed to how many the counts are in each bin. So that's it. Those are the different ways that you can organize a quantitative variable. Pretty simple, to be honest, but I want to emphasize one more time that the greatest thing that we could see is what's called the distribution. What values the variable takes on and which values are most common or most often occurring. And any of these things, histograms, stem plots, dot plots, all of them are really good at showing you that distribution. All right, in the next video, we'll talk about how to analyze and really dive into a deep analysis of these graphs.